Hello everybody. Today we will talk about delay and the dead time. Up to this point we've assumed that our transfer functions or our models do not have any delay in them. But in the real world we all know that nothing basically happens instantly. We have, even in the fastest process, even in the fastest event, we have a slight delay, a small delay that we almost do not experience. But in some cases, this delay may be noticeable. For those cases, we have to keep in mind that there is a delay and we have to adapt our control strategy accordingly. And now, for example, if you hit your boiler, your water boiler, you will see that it takes quite some time to make some noise indicating that it is heating the water. But since most of the electronics today are very fast, we have delays in nanoseconds, which are basically not even delay. But in some mechanical systems or in some other processes, sometimes it happens to be that we have a noticeable delay, and this delay is very much a part of our lives. For the students, we all, or most of us, live in Istanbul, and in this metropolitan city, you know that we have a problem of traffic. And for example, traffic is the best delay model you might see in our daily lives, because in work hours or after work hours, you see that we have a very high traffic. And if someone, for example, hits the gas pedal, if someone accelerates, the one behind that car actually has a certain delay. It takes some time to perceive that you have to accelerate, and this person accelerates, and the car behind that car even has more delay, because it's adding up. So if you are 10 cars behind, then you experience the highest amount of delay you might see in your daily lives. So this is the reason why if the traffic is not that high anymore at that point, you see on most of the apps that there shouldn't be any traffic at this hour, but there is, because this delay adds up, and it basically affects you. So in a city this large, it becomes a highly complex model, and modeling this or anticipating these may need some advanced techniques. But enough talk. Basically, today we will add some delay, some reasonable delay, only just one delay, because what I've talked about has some multiple delays, and it's basically a network of delays. And we will just focus on a basic system that is modelable with a transfer function, which is linear, but also has some delay in it. Now, we have a system that is a second order system. In this case, it has two real poles at 4 and 6, and then we have 2 seconds of delay. Well, basically, if you remember the Laplace transform, if you remember how to work this out, a time shift, a delay in time domain, corresponds to the e to the power of minus tau s, where tau is the shift in time. The shift operator, you have to go back and check the Laplace table maybe, or your Laplace notes, but you will see immediately that the delay corresponds to e to the power of minus tau s. In this case, we have tau 2, which means that we have a 2-second delay, which shifts 2 seconds in the time domain, but it's represented with e to the power of minus 2s in our case. So if you see a system that has some e to the power of minus tau s, you can immediately see and assume that this is the delay, and we have a certain delay. Now, we will use MATLAB and we will try to plot the step response of this. And then we have some approximations, because we will see immediately that the characteristic polynomial with a closed loop consisting of this system and a certain controller, or an arbitrary controller, it doesn't matter, you will see immediately that you don't have basically a characteristic polynomial anymore, because this time delay will appear in both the numerator and denominator, and this will mess up stuff. But we can go ahead and try to approximate this, and this approximation is very important, since we will see that it kind of helps us for the usual techniques that we've learned up to this point. You can use this first order approximation, this Pade approximation, and you can see that it becomes basically a third order system with a 0. So it doesn't matter anymore if you have any delay or not, because you've approximated that delay. And there are some orders to this. You can have higher orders, nth order Pade approximation. It has a certain formula. You can check it out or look it up. Here you can see we have a more complex structure that is trying to approximate this delay effect, and we will try to compare the zeros, the poles. So we basically will see what it looks like and what the approximation does, and how the system behaves. And then our second task today is to calculate the stability interval of a p-type controller using the first order, second order Pade approximation. This will help us to determine the designable controllers or the achievable controllers here, and stability will become an issue, and you will see why, and you will see how. And our third task today will be to design a PI controller for this system using the Pade approximation with 10% overshoot. Basically, it's also possible for me to skip this part even, because if you use any Pade approximation, as I've said in the previously, if you use any Pade approximation, you have a system, an arbitrary system, and you can go ahead and design your PI controller to that system. The important part to note here is that you have to try to not forget to plug this controller into the original system or model, because the Pade approximation works like the Laplace transform or the Fourier transform. It has the same mentality behind that. You have a, let's say, perfect model that is GS equals 12 divided by the poles times e to the power of -2s, which is your perfect model. And you're obtaining an approximation of this. You're constructing an approximate model, which is just for the sole purpose of designing a controller. Once you've designed your controller, you will forget about this approximated system transfer function or the model. You will just throw it in the trash and take your controller and plug it into your original plant. Now, this is very important because most of you will forget to try it on the original system, and most of you will just plot the closed loop that is approximated and not the original one, not the actual system. So this is something like going in the laboratory, looking at a, let's say, motor, approximating the model, and just plug in and trying or validating your controller on the model, not on the motor. So you have to basically check it out, and you have to basically take your design, plug it to your original motor or plant or process, and then observe the outputs and the characteristics of that. So, and our last task today will be to designing a PI controller with 10% overshoot using the Smith predictor, which is basically a different approach to the Pade approximation. So we will see basically two approaches here. First of them is the Pade approximation method, and the second one is the Smith predictor. So they have their constant pros, and we will see about and talk about that. But if you have a delayed system, most probably you will be asked to use the Pade approximation, the Smith predictor. There's a third one actually, and we will come to that in the next lecture because that's the frequency domain method. It's also possible to use some frequency domain methods to design controllers to delayed systems. Now, first of all, let's start with the first task today. Let's go ahead to MATLAB and try to analyze the system. Now, as usual, I will use the transfer function first in order to see what it looks like. Now, we can type in the convolution. I use the convolution here most of the time because it does the, because I'm a lazy person, and it does the multiplication of these polynomials s plus 4 and s plus 6 for me. So basically the convolution works like the follows. You have the coefficients of the polynomial that you want to multiply and the other polynomial coefficients, and then it takes care of the multiplication. It gives you a most probably a bigger vector because it has some degree to it. It will give you a bigger vector that will have the coefficients of the multiplicated or of the multiplication itself. Now let me define first the non-delay part. Where is it? This one. Okay. Let's run it, and we will see immediately that it is 12 divided by s squared plus 10s plus 24. Now, there we go. Now, first of all, we need the step response. So let's try to obtain the step response. We have 2 seconds of delay, and it's not possible to use these or update these so that it will have the e to the power of minus 2s data in it. So what you can do with transfer function objects is to define an IO delay, which means input-output delay, as far as I know, and you can put in the amount of delay that you have. So if I, and look closely to this point, if I update it like that, I will immediately see that there's a input-output term e to the power of minus 2s. So we use this IO delay comma 2 in order to let MATLAB know that we have 2 seconds of delay. We give the non-delay or the fraction part as usual, and we provide the delay data as the next arguments. Now I can go ahead and use step, so it's fairly easy, and I will see that we have the system response. Since I have 4 and 6, which are real poles, I can see that I shouldn't have any delay. I know that the multiplication gives me 24, and this is the constant term in the denominator. So 12 divided by 24 gives me 0.5, which is the final value of this system, or the steady state value. I can use the final value theorem on this system. Since e to the power of minus 2s, if s tends to 0, you will see that this will tend to 1. So basically it doesn't matter if I have some delay. I will have the same steady state value. I will have the same settling time, overshoot, all the time domain characteristics. But if I calculate the settling time starting from 0, of course I should add up 2 seconds to it. But the rise time will not be affected from that, because settling time, as the definition says, is the point where, or is the time instant where the response settles down and enters a certain error band. So basically I have to take this part also into account if I'm using settling time, but I can also view settling time beginning from 2 here. If you are given any settling time and if you have a delayed system, you might go ahead and ask what is the real thing here, but note that what is the real settling time. since we have delay, should I take it into account or not? But remember that the settling time formula has only zeta in omega n in its denominator, 4 divided by zeta times omega n, namely. And if you are given a settling time, you are basically given the data that's about zeta and omega n. So delay will be given separately, so don't take it into account unless it is told so. So if you have settling time and a delayed system, most probably the delay part will not be added to the settling time. If you have 2 seconds of settling time and 2 seconds delay, basically what I mean by that is, of course, the value will be 4, but your settling time will start from 0 and enter the point here. So keep that in mind. Now, I can also see that my time shift happens. I might go ahead and define also GS0, which is the non-delay part. So, and I can also go and try to compare them. Let's say this should be black, and let's let MATLAB decide the other color. And you can see now, if I plot both this transfer function and this transfer function, I can see that it has the same shape. It's basically the same response, but only shifted 2 seconds because we have 2 seconds of delay. Now, this doesn't seem like a problem, but in order to see if it's a problem or not, we should go and we should define our system using the symbolic toolbox. And let's say we want to design a p-type controller. By the way, you can pass some extra argument here for variable definitions using the symbolic toolbox. You can tell the sim engine behind the scenes that this is basically a real valued unknown, because it might become important in certain cases. And let me demonstrate it to you. Let's say we have m here, and I want to have the conjugate of this. Before I start this part, let me show you this. I might have k and the conjugate k, and I might have m and conjugate m. Now, if I run this, you can see the difference here. I have told the sim engine that k is real, so the variable k and its conjugate is the same because it doesn't have any imaginary part in it. But I didn't tell the sim engine anything about m, so it assumed that it might be a complex valued unknown, or it might be a complex value, so it might have an imaginary part in it. So I should write the conjugate as conjugate m. So this might not be a big difference, but for some problems, and this is basically for the frequency domain more, because we are not using that much complex valued things here in the time domain, but in the frequency domain, that this may give you a difference. Or sometimes the MATLAB solve command will give you extra solutions that are not necessary, or that we don't even need and will not use. In case of omega n, if omega n is real, then you should maybe go ahead and tell the sim engine that omega n is real, because it will narrow down to the real values. But in other cases, it will give you all the possible solutions in the complex domain. So that's that. So I can tell that this is real. And let me first define my system here. I know that this is s plus 4 times s plus 6. So I have also the delay part, so I might go ahead and x to the power of 2 times s. And let's say pretty and GSS here. Maybe collect also. It should arrange the s values here. And let's try to calculate a closed loop where we, as usual, use this feedback structure and calculate the closed loop's transfer function, because we need this in order to change the behavior here so that we have the closed loop settling time overshoot, whatever time domain requirement is given. So let's compare that. Now the first one, and if I say collect S or something, you can see that it immediately calculated this. Maybe collect is not a good idea. Let's get rid of it. Exactly, this looks a little bit better. This is our system, our plant, 12 times e to the power of minus 2s divided by the poles. And if I'm calculating a closed loop, and you've already seen basically it, if I calculate a closed loop, I have this expression here. Now, I have e to the power of 2s, and I have the same here, and the same here. If I'm, maybe collect should go away too, but I'm not sure if it will give the same. If you pay attention to this term here, you don't have e to the power of 2s, which means that if I'm going to factor e to the power of 2s out here, I will have e to the power of 2s minus 2s here, and as usual s squared and 10s and 24. So it is a weird closed loop, and this doesn't help me out. But maybe I should try my luck with the, or simplify fraction was a function, I guess. If I use that, and pretty, of course. No, doesn't give me the effect that I'm looking for, but I should maybe try my luck in using the num_then function that will separate the numerator and denominator for me. Let's have the denominator. And you can see now I have 12k and still the same thing. So basically what I mean here is if you factor this out, you will have e to the power of minus 2s. If not, this is not a polynomial. Because if you remember the definition of the polynomial, it should have the s term and all the powers of it and a linear combination of only s terms. If you have a different function than s, or its linear or its powers and the linear combination of them, then you don't have a polynomial. So we have e to the power of 2s, so this is not a polynomial, but this is called a quasi-polynomial because it looks like a polynomial, and it has some polynomial terms in it, and if I fix s to a value, I will have a polynomial or a real result at least, but it's a quasi-polynomial. So I cannot work with this because I have no methods that will calculate me the roots of this, or I'm not able to use the coefficient methods here. So what can I do? Well, basically the first thing here is to approximate this term e to the power of 2s or minus 2s, depends on what you need. So let's basically let's go ahead and approximate this. So I will get rid of this. Maybe I should also separate this so that I have tf here 1,1 and this. So what I've written here is basically the delay term itself. You can also define the delay on its own, and you can see that if you give it one gain, a gain of 1 and a e to the power of minus 2s, then you will have the pure delay here. So I have now the same system. The only thing is with GS0 I don't have the delay term, and with GS0 times the delay term I have the full system. So I've divided the plant into its subparts here. Nothing changed, and you don't have to do this, but I will use it later. Now, if you want to use the definition and At this point, I will use basically, let's say, GS1, which corresponds to the first order Pade approximation. Now I will use this term times, this time, instead of the delay, I will plug in the approximation that we had there. So let's define tau as 2 here, and let's go ahead and define it here basically. Let's say this is tau. So what I have to do here is I have to use this expression, and I will multiply the non-delay part with this approximation instead of the delay itself. So I have minus 0.5 here, minus 0.5. Oh, it doesn't work like that. Okay. So we have minus 0.5 and 1 and the same. But this should be positive 0.5 and times tau basically, times tau times tau. So this is the approximated part. Let me go ahead and use the second order approximation in order to define the second order approximated transfer function, which should be called GS2. Now I will add tau square divided by 12. You can see that the first order part is the same. You have only tau square divided by 12 as the highest term. Since this is the highest term, and since I have 3 coefficients, it starts with S0, S to the power of 1, and S to the power of 2, so it's the same transfer function if you pay attention. So this should be the second order approximated part, this should be the first order approximated part. Now I can see what happens here. Let's have all possible transfer functions here. Now we can see that a first order system without a second order system, a second order system without a zero with delay, and if you use the first order approximation, it will add 1 pole and 1 zero, because this is basically the transfer function that corresponds to e to the power of minus 2s. This will give me a 1 0 3 pole system. If I have the second order Pade approximation, if I use that, I have 2 zeros and 4 poles. So and as I've told you before, and there's a formula, I didn't provide it in my solution manual, I guess, but if you, and I will show you what the expression looks like. If you type in Pade approximation, you will most probably find it in some textbooks or in your notes. And you will see that if you increase the approximation degree, you will have a higher order system. So we've talked about this in the previous lessons, basically. If you have a higher order system, the control problem will become more difficult than it is for lower order approximations. So having a higher order, and we will see, is not that much desirable. But before we talk about that, what is the step response of these two systems? What do they look like, and how are they compared to the first one? And as you remember, our first task was to plot the step response of the transfer function, then define the Pade approximations and compare all the step responses and pole zero maps. Let's go ahead and do this. Now, I might go and define my time here. Since I know my settling time was about 2 seconds, 2 seconds delay, 4 seconds. Let's have 6 seconds of simulation with a precision of 0.01. Since I have time, I will omit the time term here, and I will calculate the step response using this here. Now this is the original response that I'm looking for, because I'm using GS here. The only thing that I will do is I will use the approximated versions here. And then let's open up a figure. Let's have a subplot. So let's have multiple axes here. Let's have one row and two columns, so they will be side by side. And the first one of this, hold on and grid on some visual setup. And let's plot it with a color of black, with a increased line width. And let's give it a display name of delayed system. Looks fine, so let's go ahead and use Y2 with red. The display name is first order Pade approximation, and basically this should be one, the second order Pade approximation. Let's have X label as time, because X axis is time. Okay, this looks better. And then Y label is the output. And let's give it a title. Comparison. And that's basically it for the first one. Let's have a subplot, the second one. Instead of this, let's get the poles and zeros. You can simply do this by PS poles PZ map. But if you equate it to this, or if you're catching the output like this, so you will not have the plot itself. Let's first of all try this, by the way, and let's see if we can. And we can, but GS has some delay term, and it doesn't use the delay part here. And we will come to that. Now, so this is a better version. If I type in GS0, I will have this a little bit more correct. So let's have Z1 and P1 if we use GS1, and P2 and Z2 or Z2 for GS2. Now, instead of these, I will plot the real PS and imaginary part of PS with KX and line width 2. So as you can see, I like to use my own code instead of the in terms of visual things. I like to code it myself because I can. Oh, by the way, I have given it this color. Maybe blue is better. So this one is red. This one should be blue. I like to customize my plots as much as possible. So seems to be alright. This is the real part. I guess it can use sigma and 1 divided by seconds. It's the same, but this time it is the imaginary part. This is J omega n, and this is the pole zero comparison here. And I have forgotten to say legend show. There we go. We could have given it the same display name, but since we've kept the colors consistent, it's also good. So, or maybe let's give it, because we've used the legend here. So, and then this one here also. And I don't need the, or maybe let's don't touch that. I didn't copy the display part. display name part. Okay. Now, let's keep it here. Now we can see what the responses look like and where the poles and zeros are. Basically, my two poles are here at -6 and -4. That's not a problem. I have a 0 at -1 for the first order Pade approximation here. And I have two zeros on the right hand side because I can on the left basically. This is at -1. This is at minus. I should have. Let's check it first. minus 0.5 s. So I guess there is a slight problem here. I did plug it in, and GS1 has minus. So why do we have this problem here? Oh, we didn't plot the zeros. Okay. I did forget to plot the zeros here. And you will see why I questioned this in a second. This time we will use some circles, and therefore maybe dropping the display name here is a better choice, since it will show it multiple times. Let's get rid of these. Okay, so that's better. Now, since I know the values here, -1 and 1, maybe I should plot the axes too. Let's plot a line that will show us the j omega axis here, and this line should be between for the x values it will have 0, for the y values it should have 1, and we will have a black dashed line here. We will repeat this for the real values. My real values are -6, and I'm not sure what the limit on the right. Oh, it's 2. -7 and 2 is a good idea here. -7 and 2, and without any y values. Now I can see it a little better. Now this is the origin, and you can see that all the zeros are on the right hand side. And for the first order Pade approximation, what we've done is basically we've kept these poles, all the poles, because we don't touch that part. We take the part without delay as it is, and we've added one pole at -1 and one zero at 1, because -0.5 times tau, since tau is 2, is equal to 1. So at -1 and 1 we have a pole and a 0. For the second order approximation, we have added two poles, which are complex conjugates, and two zeros, which are again complex conjugates. And their real values are exactly the same. And you can see that if I'm not sure if I'm able to click it, but we can see it by using, let's say, Z1 and P1 here, Z2 and P2. So you can see that the complex conjugate values are even the same, because we use the same polynomial with a slight change in the sign in the polynomial. So it has the same solution but symmetric. Now this symmetry is very important, since all the poles and zeros will be placed symmetrically, and we will see that. In terms of the step response, I can see that the approximation methods for delay is proposing overshoots and undershoots here. So this is basically, or let's call it oscillations. That's a better term. In positive and negative waves, we are trying to approximate the response, and the delay part it consists of this sign, or this is not a sign. This is basically an overshoot and undershoot. Now, for the first order, we have an undershoot, and then it tries to rise and try to have the same step response. But since we have added only one undershoot, and we didn't start at this point, we don't have the best performance, and it doesn't look that much like the original delayed system. In the second order system, we have an overshoot, some time passed here, and then we have an undershoot, again some time passed here, so T1 and T2. So the total here is less than the delay part, but it has some delay. So it corresponds basically to delay by using some waves and coming back to its starting point. So this part will give us T1, and this part will provide us T2. So the sum here is a better approximation of the delay too. So basically what the approximation tries to accomplish here is to add as many as overshoots and undershoots as possible, so that we have a consumed enough time that will correspond to the delay part, the dead time. So, and then when it's again at its starting point, then we will have the transient effect that tries to emulate this effect here. The only thing that is the same with the original delayed system is the final value, because we are placing them so that we don't change the gain of the system in steady state. So it should settle down to the same value. Now, it is interesting, and if we use some higher degrees, it is going to work better. And I've shown you how to get the approximations, but this is not the ideal version of it. Since I know the expressions here, I wanted to show you how to do this manually. You can also tell MATLAB to do it for you, and there's a Pade function here. You can say I have GS and I want the first order, and let's use Pade and the second order. So if I run this, as you can see, I have the same transfer functions and I have the same structure, and everything is the same. I had -1 and 1. I had this symmetric structure here. So let's get rid of this here. So we can try to use the Pade function here. And if you type in help Pade, you will see that it will give you the numerator and denominator here. You can also use the system and n in order to get the approximated system. So, and maybe I should adapt my code a little bit. So that I might do some nice simulation, and I might go ahead and prepare a nice graphic that will help me. Now let's take this part here and let's place it somewhere here. So let's have some initial GUI stuff here, and I have defined this. This will give me sort of a method, so that I will not call figure 1 and subplot again and again, but I will use AX1 in order to tell MATLAB to use the first plot that I've generated here. So it should then go ahead and use this here and this here. Now let's get this here, and you can use every GUI related, plot related function, and you can provide the first argument as the graphic handle here. So this should basically create the first plot that is needed on the system with black, and arrange the X labels, Y labels, title, etc. And then I will plot my my Pade approximation, and I will do the same for the second one. And let's get this one too. So let's plug it in here. I need basically this part too, which should be, let's say, after this. Let's do this. Okay. And the axes are not that important. I will change that later. I might take this part here. I want to have this part also, and then this part too. Now we will define the time once we are done with these here. Now the code left, that is left here, but first of all I should finish this. Basically, let's have AX2, and let's tell plot to use AX2, and then this is the label of the second plot. Basically what I'm trying to tell here is that, so this is Y label, by the way. So, okay, so the axis, I will come to that later. Let's tell MATLAB to use this. Oh, this is also AX2, AX2. Now you can see what I'm left with. So after the time definition, this code basically repeats here. And what I'm trying to do is I'm trying to build a for loop of degrees, let's say 1 and 2, to ensure that it is working. And you need to use these graphic handles here if you're using a for loop. So if you use figure 1, that's all okay also, but it will cycle through all the figures. You will see a animation that is not needed. So let's get rid of the second part here. Let's get rid of this, of this, of this, of this, and this here. So, and let's change the display name here. Let's make it something simple, n equals and num to str. This is the degree of the approximation, and it should be n here. This should be n, the nth order Pade approximation here, and once I have that, I will get the nth order response. I will plot that without giving it a color, but that will be a slight problem because and it's not possible to solve that. Well, we will come to the colors later. The nth order GS, and then PN, and then ZN. It's not necessary to change these, but it helps me to explain the code a little bit. So basically what I'm trying to do is I'm trying to get the nth order Pade approximation. I define the system, I get the step response using step, I plot that on the first plot. Let's get rid of this white space. And I'm getting the pole zeros using this function pzmap, and I'm plotting the real versus imaginary. So I'm placing them on the complex plane basically, and I plot the poles and zeros that are the poles and zeros of this nth order approximation. Before I start this loop, I go and what I'm doing is I'm using the original system here with delay. I'm getting the step response, plotting that, arrange the labels, and then I go ahead and get the pole zeros of this. You can type in GS or this, it doesn't change, but the delay part doesn't give the pole zero part of itself. And I plot them too and arrange these. If I hit run here, I might have a problem. Okay, I have defined T, but it's too late because I'm already using it, so I should go ahead and define it before everything happens. Now, my slight issue here is that I am not matching the pole zero colors for the same approximation, and therefore I might go ahead and define a, let's say, I might go ahead and define a linspace vector here, and I have to change this into I equals 1 to the length of the order, and the order is equal to 1 and 2. So linspace, let's start with 0.2 to 0.9 using length or terms. So this part is not that necessary, but in order to state my in order to make some statements, I need this color transitioning code, which is not really important, but just for the sake of this tutorial here. This is the ith element of this lum here, so n, and then n, and then n. The only thing that I'm going to change is that I need to provide a color here, and you can type in color and provide a RGB vector, and this RGB vector should have 0 and 0. Maybe let's RGB, let's make it blue, and this lum element here, oh, basically it was the order here, I'm sorry, the lum I comes here into play. So what this does is it creates a transitioning, because we are increasing our color value from a certain starting point to an ending point, and we use exactly n elements, or exactly the amount of elements that has order in it. So every order will correspond to a linear value in this array here, or in this function here. So we will have a light blue, and if we have a less order, oh sorry, it's the inverse. We will have a dark blue if we have less order, and we will have lighter and lighter blue as the order will increase. So that's the effect I'm looking for, and I can now safely go ahead and provide this color here. Maybe this is a better word. Okay, so everything will have the same color. If it's the same order, it will increase the brightness of its blue color, so I will see which one corresponds to which one, as you can see here. Now the starting point, this is a blue color, but it's not that differentiable from the original one, but it doesn't matter. You can go ahead and increase this value here, so we will have a lighter starting point and a blue here at the ending point. So this is the most blue you will get. So that's that. And I can, for now, use the same thing. Now the nice thing about this is I can increase the order, and it will give me the approximation that I'm looking for. So you can see now it has 3 cycles. The most light blue one will be the highest order. So I might also do a little thing that if I do 1 minus, I will have 0.4, should be 0.6, and then 0.1. Okay, maybe we should also use another channel to this, so it will have a different effect on every color. Now it's not blue anymore. we will have a certain transitioning here. Maybe I should use the same loom to the not sure about that. Let's try it out, but I'm not sure. It might be again a bluish color, but a more different transitioning here. I don't know. Let's apply it here too. I did forget that one. Is this better? Arguably. Let's leave it at 0. Let's live with that. Okay, it is kind of good. So now I can see now that I have 3 oscillations here, or 2 undershoots, 1 overshoot. So I'm consuming more and more time. This is the delay part that's modeled, or this is the delay that is modeled by this first one here, and then this is the second order Pade approximation that is modeling the delay. And the higher the order gets, the better it gets this approximation here. And you can also see that this rising transient behavior here is a little bit more like the original system, but still not satisfactory. And let's go ahead and try the 4th order. And it increases the amount of time that's consumed by these overshoots and undershoots. And another aspect here, I'm not sure if you're following it along, but you can see that the amounts or the peak values are decreasing here. So we had this large undershoot because it needed more time to consume. So this when this period here is increasing, then basically this this wave is here peaking more and more. If we have a decreased interval or period for this wave here, then it will not peak that much. So basically this maximum peak in this area is decreasing, and our rise time or our increment here basically approaches the system a little bit more. So I'm not sure, but can I do something like this? Only the 3rd and 4th order should be shown here. Okay, I can do that. And you can see now that we have an interesting pole 0 map, because we have only 2 values here. I can see now that we have 3 zeros here on the right hand side, and the symmetry is preserved. You have some symmetric stuff here going on. So if you have 4, you're like on a omega n kind of circle, and then you have this symmetry here again. So, and these poles are the poles of the system, so that's important to note. Now, what happens if I increase it a little bit more? And I'm not sure, but I can also give it, I guess, a single value here. And you can see now that we have 5 zeros, 5 poles, and 2 poles of the original system, which makes a 7th order system with 5 poles. So this is not an easy system to use for design, by the way, but these oscillations are helping so that I have basically a good response that looks more like the system here. So if this is an approximation, it's not bad. It's way better than the first one. So I'm not sure, but I might be able to do this here. Hope I'm able. I can give it the 1st order and 5th order, and I can compare this. And you can see that the approximation performance is dramatically increased if I have the 5th order Pade approximation. So that's compared with the 2nd order. The 1st order is obviously the worst approximation, but the 2nd order here is also not that good if it's compared with the 5th order. But the second order has 2 zeros on the right hand side and 2 poles on the left hand side and 2 poles of the system, which is a fourth order system with 2 zeros. And the fifth order is a seventh order system with 5 zeros. So basically, the situation becomes better in terms of approximation if you have higher order approximation, which is kind of trivial to say even, because the level of approximation gets better if the order of approximation, obviously that's the case, but it becomes harder to design a controller for this system because it has too much poles and zeros. And keep in mind that these poles and zeros are close to the j omega axis. So if I'm enabling this here, and if I plot this, it's obviously -4 and 4. I should change maybe 4 times this is a better approach here. Now you can see that this is basically on the right hand side, and 4 times this is, we will twice something like this. We will have twice amount of space on the left hand side, etc., etc. Now I can see that I have too much going on near the j omega axis. And remember that if you're plotting a root locus, the first rule is that all poles will eventually reach the zeros of the open loop. So all open loop, or all the closed loop poles will start at the open loop poles and will tend to the zeros. Maybe finite zeros, maybe infinite zeros, depends on the plant, but I have placed 2 zeros on the right hand side for the second order approximation, and I have placed 2 poles symmetrically on the left hand side. It is good that I have placed them on the left hand side because they are stable, or this approximation is a stable approximation, but they will tend to 0, and most probably the poles that I've placed will approach these zeros that I've placed by the approximation. So most likely this pole will tend to this 0 and this one will tend to this 0, and we will see that in the upcoming tasks. But if there's a high order system, it becomes worse. So all these poles most probably will try to reach these zeros. So I will have a narrow, and I'm not sure about that, but if I have an interval, it will narrow down. Because the more poles and zeros are in this region, the more crossing over will happen. So, and we will come to that, and it will become very, let's say, enjoyable and interesting in mind. So, what about 10th order? I will have a 12th order system with 10 zeros, which is a nightmare, but you can see now that we have a certain radius to this, and a good thing here is that I am also increasing my radius, so that's I guess good. And you can see the approximation performance on the left. I have some oscillations and then a big jump that is almost the same for the part that is after the delay, and it has almost the same amount of delay here. Not bad. So maybe the 20th order, which is basically a nightmare at this point. And you can see now it fades the maximum peaks or the maximum of the peaks of this region decrease drastically, and they're kind of around this stable point here, and then we have the same behavior, and my poles and zeros are nicely laid on my complex region. So I can go ahead and have 30 or have 50 even, but at this point I cannot design anything for this, and I'm starting to start over with a new thing. So interesting stuff happens here. I'm not even able to tell. But you can see it almost vanishes. This region is almost the same. You have to zoom in at this point to see what's happening and what's going on here. You can see that there are oscillations. And you can see now that basically if you have a real system, a real world application, this is good enough, because your model and your system will have a similar relation, since there will be noise and high frequency components to it. You will have most basically something that has sort of high frequencies embedded to it. So at this point you have a good approximation. But as I've told you before, it's not a good idea to use this high of an approximation, and you will see if we are even able to reach the third order, because it is very hard to use these. But let's compare 1 and 2 and leave it at this point, because this is traceable. You can see here and try to guess what is going on. But if you have 50 poles that's coming from the approximation and 50 zeros, that's not usable at this point. Now, this was the first task. I have adapted a little bit, but it gives us an idea about the approximation. You can see that the steady state gain will always remain 1, because the constant terms are 1, and then if you're increasing the order of the approximation, you will be adding the s to the power of n up to s to the power of 1. So you're adding those terms, but if you plug in S0, this will give you 1, which should be the case, because e to the power of minus tau s is equal to 1 if you're plugging in s equals 0. So this is nice. Now, last but not least, maybe I should show you the Pade approximation. And if there's Wikipedia, and I hope, oh, that was not what I was trying to do. And you can see this is Henry Pade, by the way, and given a function f, two integers m and n, approximant. Maybe I should have read what it Pade approximation. I should have looked up it before, but I guess this is what I mean by that. So now, which one is it? I'm looking for the one that we are looking for, and here it is. A fifth order example here is given here, and you can see now this is 1 if you have no order, which makes sense. But if you have the first order, you are adding 1/2, so 0.5x x plus 1 and 0.5x minus 1. And 1 divided by 9, 1 divided by 9. But this is e to the power of x. So if you use minus x, these will be a little bit different. And unfortunately, there is no e to the power of minus here. I did not write it down. Maybe it was a good idea, but let's try this one. Do we have here something that looks like that? But nope. Let's say time delay. Maybe MATLAB is helping us out. I don't know. Does it? It should. Sometimes it shows you what it looks like. Maybe we should use this here in order to. Was it about Pade? Oh, it's not about Pade. I didn't pay attention. Well, unfortunately, MATLAB doesn't help us out here. What about Wolfram? Is that helping out? demonstration code. Maybe it will show us. I'm not sure, but I guess I should add this. It's only giving the part that I'm providing here. So maybe I should have added the approximation, because this is not shown directly. And you can basically do the same here. Give some orders and look for it. But interestingly, I was not expecting it. So there we go, I guess. This should give us... Yeah. I hope that this is the approximation that I'm looking for. I'm not sure, but most probably I will edit, and if I forget it, please remind me that I should add this if I did. Well, okay, it's not that important because we will most of the time use these two orders for design, and there is a Pade function that will give you the approximation, so you can work it out basically, because we know what term we are trying to add. But if this is 2, it's hard to work it out by looking at this. Okay, hope that the first task here was helpful, and you hopefully understood the mentality of the approximation. Basically what we're doing is we are adding an approximate transfer function instead of e to the power of minus tau s, and basically we have a symmetric structure, and we are trying to use some overshoot and undershoot in the region of delay to approximate this delay effect. We are basically going away and crossing, and basically what we're trying to do is we're going away, we're coming back, we're going away, we're coming back, and we are consuming time so that it kind of models the effect of delay. And it should not affect the transience of the system that much, but if you don't have high order approximation, this approximation is and seems not to be a good idea, because the effects are roughly modeled here. So the higher the approximation, the better the performance of the approximation, but we will see if it's hard, if it's tough to design and to use this stability interval, etc. Now we are at this second task where we are asked to find the stability interval of a p-type controller using the first and second order approximates. I'm basically extending it to the nth order, using the obtained intervals, compare them using original delayed system. Now let's copy this whole thing, let's paste it in here. Nothing changed basically, but I will first of all comment this out here. Now let's call it run 2. Now if we have this delayed system, let us just run this part here. Did I run it? I guess. Okay. If I have such a system, GS, and if I type in R locus, which corresponds to root locus, basically, I will get an error. And MATLAB tells me what the reason is, and what the error is, basically. The R locus command cannot be used for continuous time models with delays. So this is an important statement, and you should keep in mind that it is really important to know what you're trying to do. So let's raise the question, how many poles has our system? And you've seen that it kind of generated, MATLAB kind of generated a numerator and denominator that was a quasi-polynomial, and we've seen that some terms included this e to the power of positive 2s. So keep in mind that e to the power of 2s is somewhere in this quasi-polynomial for the characteristic quasi-polynomial, let's say, or denominator of the closed loop system. So basically, how many poles do I have here? And if we want to answer this question, we might look for the Pade approximation as an answer. And we've seen that, let's say, for example, for order 30, it was a good approximation. So basically, at least we should have 30 poles and 30 zeros for the system to be approximate. So, and if we increase the order, the performance will better. So I might assume, and I can say that this closed loop characteristic quasi-polynomial has infinite poles. And this whole transfer function has infinite zeros because of this e to the power of minus 2s, because of delay. So if you have delay in the system, you most probably will have infinite delay, infinite poles, infinite amount of poles, and infinite amount of zeros. So our locus is telling you that it doesn't know how much finite zeros and poles this has, because we have finite poles and zeros here, but infinite amount of finite poles and zeros. Our locus, or the root locus algorithm, is not capable and able to calculate how many poles there are and how many zeros there are. So if it doesn't know how many there are, how is it supposed to place them first on the complex plane, and then try to represent the movement of them? So there are no finite amount of poles and zeros in the system because we have delay. So our locus is not available for delayed systems. But it proposes you to use the Pade approximation, because we will kind of take some poles and zeros from this infinite amount of pole zero pool, and we will try to approximate it to the original delayed system. So I'm repeating this because this is very important. Keep in mind that we don't have countable, let's say, poles and zeros. Because there are infinite amount of them, we are not able to plot a root locus. So this is very disappointing if you think about it, because I mean disappointing in the sense that the most simplest tool, root locus, is not available. This is unfortunate. But we can use Pade approximation to get an idea. Not the exact value or exact interval, or the root locus analysis or synthesis will not be exactly the same for the system, but it will be enough for us because we're engineers and we have some tolerances. So after a let's say finite degree that is reasonable, it will be almost the same. But since our usual design method is also not exactly applicable to the real world system, because we have assumed that the system is linear, which is not the case in most of the real world applications, and since we have neglected most of the effects that are very important in real life, let's say it becomes heated, let's say it becomes affected by a magnetic field, most of the things, most of the internals of any plant or process most probably will depend on these properties, so we are neglecting most of them. So it's also okay to at some point neglect the high order Pade approximation errors, and we can still just be fine with this. But we are not able to directly use the original system to construct a root locus plot. That's important. Now, but as I've told you, we can go ahead and use the root locus plot. So maybe I should get rid of the subplot here at this point and work with certain with multiple figures here. Let's have the same thing here, and that's the only line that I should change, and I can just get rid of this part here. So that's the ease of this method, and I might want to still have this here, but now I should open figure 2. So order will be, let's say 1. And I will use AX to GCA here. I guess our locus is applicable or can use this here. We will see in a minute. Now I can use 4 here again. This is not necessary. And this will be the order, the nth order Pade approximation. At this point I can just get rid of these. Maybe color can be useful, I'm not sure. But I guess it's not possible to use it for root locus, so let's make just order equals 1, and let's get rid of these here, and let's make it n, directly n. So that looks a bit better. Our locus of GSM. That's it. Now you can see we still have the step response here, and then we have this root locus here. And keep in mind that the root locus starting points are and should be the same with the pole zero maps that we've generated in task 1 in A. So in B here we are generating the root locus plot, and this is basically our root locus plot, and it has some similarities. And you can see we had 2 poles here. We are adding 1 pole and 1 0 because we are using the first order approximation. Now I need to find this point here, the j omega crossing here. What was that? Yeah, let's get rid of this. So if I click this and drag it to this point here, I can approximately see that it is something around 2.3. So basically the system is stable for the interval 0 and 231. That's what this first order Pade approximation tells me. Now, this is a nice information, but what about the second order approximation? Let's keep in mind that it was 2.3, something around that. And what happens if I have the second order approximation? And we can see that we have a different root locus structure here. These poles are approaching each other and moving so that we have a 90 and minus 90 degrees angles here. So this point, somewhere around this point here, should be, there we go, I've clicked it. So I can see now that it is almost 2.14. So let's note that, 2.14. If I have a higher order approximation, 3, what will be, and the structure is again changing, and we have an interesting structure, by the way. Now what happens if I click this and drag it here? I can now see that at 2.14 we have, again it is 2.14. So basically after this point I should get 2.14. This seems to be the case here. And I can validate that by using, let's say, 5. I'm scared to put in a high value because there will be too much crossings and I don't really know which crossing is has the minimum here. So another problem here even is to look for all crossings and take the minimum of them. So you get the idea, but we can basically skip this root locus part, and we can just take these values and try to look for the closed loop system, because it tells me that the closed loop here should be stable up to the point where we have a critical gain of 2.3 for the first order and 2.14 for the higher orders. So I can just try to check what the closed loop response looks like. And let's try to look it by using the closed loop. So let me create another figure, and let me use this here. Let's copy and paste this. Here I will use TS equals feedback, and I will use, let's say, 2.3 and the first order approximation. So times Pade GS comma n, and 1, because this is unit feedback. So I know these values. So first order Pade approximation. So let's not take, say n, let's say 1. This is a first order approximation. I will have the feedback. I get the step response of TS. I will plot that, and let's say this is n equals 1. So num to str again. And there we go. This should be 3, I guess, since we have AX2 here. So AX3 again, there we go. Maybe hold on grid on. There we go. Now, interestingly, my time vector is not sufficient. Let's have a, let's say 20 seconds should be. But you can see it is kind of trying to reach a point. The reason for this, and maybe n should be equal to 1 here again. So we have a nice analysis here. Now we can see that at this point we have a very small zeta, very small friction, very small zeta value damping. So it takes some time, quite some time to get to steady state. And you will see that it fades out basically. Now, let's go ahead and try the second order. And let's use this too. At this point, for the same value of 2.3, you can see now this is an unstable representation. Step response, basically. So maybe I should decrease the interval value that I've seen here, and this is even closer to its critical value, because at the exact value I should have a perfect oscillation, but at the stable upper bound I have a very low zeta value in this case, and you can see it again goes on to try to fade out basically, but it takes quite some time. So now we've seen that the first order Pade approximation gives us 2.3, and if you use the Pade approximation you get the oscillation that you expect. But if you use the second order at the same value, you don't get the same effect. It will become unstable. So in that case, we use 2.14, which is basically a better approximation of the critical value. We get what we expected here. So if I use the third order, I can see that it works again. If I use for the fourth order, the fifth order. This seems to be a good point, good approximation of the critical value. Here, if we have a 10th order, let's say, approximation, we can see that it kind of works, because we have a satisfactory response that corresponds almost, not exactly, to the critical point here. So, but it's good enough. Now, keep in mind that I did use the Pade approximation. If you stop here, then your validation process is not done, completed, because as I've told you before at the beginning of today's lesson, if you go ahead and look at the motor in your laboratory and take a note, and this note includes all the process information, all the transfer function, the model of the motor. If you're approximating this model even further with using the Pade approximation, and you're looking for the stability interval, you're having in stability analysis here. If you stop at Pade, you are skipping basically the part where you should go to the motor, apply this closed loop K, and observe the output. So basically what we have to do is, at least we should try to use our, since we don't have a motor, we don't own the system, so at least we should go ahead and use the best model, or the closest model to the plant that we have in hand, which is the delayed version. Which means that I should get rid of this and plug in the system itself with GS, which has delay in it, the non-delay part times delay part. So this is the best model that I have in my hand, in my analysis, that I can use. So hope that we will see the same effect, and we do. So basically I can assume now safely that this system, safely in bounds, because I have only this and not the system on its own, I can see that 2.14 is a stable upper bound for this system, and most probably 2.15 or 2.145 is the actual critical value, something around that, but this is sufficient. Now, if we had the bound using Pade 1, first approximation, you can see that the original system gets out of control. So using the first order Pade approximation is not suitable for this system. But starting from the second order Pade approximation, the interval gets closer and closer to the delayed systems interval. And by this root locus analysis, I can see that I cannot directly use the root locus of the system, but I can use the approximations and the root locuses of those approximations, and I can go ahead and make my analysis to a certain point and try this on the system. And if this is sufficient, if this is usable, then I'm okay with it. So that's basically it. Now, but keep in mind that you should try some Pade approximations sequentially. You should start with one value, go ahead and check it out try it on the system. If it's not a reasonable response, then go ahead and use the next order approximation, and then try it again, and then repeat this process up to a certain point where you are satisfied with your interval or your design. Now, as I've told you, I might just skip C, because the only thing that I'm going to do in C is I will type in Pade and I will get the approximation, and at that point I will design the system with 10% overshoot. I will show you from this PDF, because I have the solution there, and it is already a long session, so let's do not increase the amount by repeating stuff that you can already check out in my previous videos, or just by looking at the solution, you will see what the steps are. So now the Pade approximation is very important, because it is very handy in terms of analysis and design, because you can go ahead and use the lowest possible Pade approximation, start with that as and use this as a starting point. Go ahead and make your analysis or synthesis, apply it to the system, check your requirements. If it's sufficient, then you can stop, but if not, then you can increase your Pade approximation degree and repeat this process over and over again up to the point where you're satisfied with your results. And so it gives you the opportunity to use everything that we've learned to this point, and it basically uses its own approximation method and includes the delayed system into our tools. We were only able to use linear systems without delay, single input, single output systems, linear time invariant systems, and stable systems, or for certain methods, unstable systems are also stabilizable in bounds. But we were just able to use those systems for design and analysis. But at this point, we are including the delayed systems. So it's very nice to have this approximation method. Now we will see a different method, which is not an approximation, but which is a different approach to delayed systems. Now we have something called the Smith predictor. But this time with the Smith predictor, we suppose that we know the system model very well. So a first step requirement is to have almost an exact model at this point. And a method that we've seen is kind of like the Smith predictor, or Smith predictor is kind of like that method that we've seen before, and that's the model matching controller. Because model matching controller uses the model itself and assumes that we have a close representation of the actual plant, and we use the inverse in our controller. So we are matching the model, or we're matching the poles and zeros, and the zeros on poles, so that we are getting rid of the system poles and zeros, and we place only necessary poles for the closed loop that will be generated and is predefined at the starting point. That was model matching. In Smith predictor, we place the plant, the original plant, we place a model of that original plant that is close to the plant, and we place the non-delay part of the model. And we have a certain connection there. We construct a connection that is very special, and the name is Smith predictor, therefore, that gets rid of the effect of delay, and by sort of canceling it out, but not with the inverse. So we are not multiplying anything with e to the power of 2s. We will never do that because that's not reasonable. But we are kind of subtracting the delayed response from the actual response and adding the response that is without delay. So then we use that as the feedback and we design our controller as usual. So I will show you the best figure that I have kind of found here. Now, just look at this, the top one here, not the other ones. Just look at this here. I know that this is not the transfer function representation, but this is not that important because this here is your delayed system, and basically what you see here with B and C and this Si minus A inverse is basically the transitioning from state space representation to the transfer function representation. So basically this is a transfer function, but it's not that important. Almost a transfer function. Whatever. The general structure is the same with the Smith predictor. That's the reason why I'm showing you this. Now we have the delay term here. We have the non-delayed part here. So this is basically that motor in your laboratory that you have. This is this doesn't exist as the mathematical expression. This exists as the physical correspondence. So this is the motor itself. But the second one is the model that is purely mathematical. So this doesn't relate to any physical stuff. This is trying to approximate the model of the plant, which is shown here. And then I have a non-delayed part of the same representation. I'm not using the e to the power of minus tau s. I'm just using the system transfer function. In our case, it will be 12 divided by s plus 4 times s plus 6. But here we have the delay parts too. And this is basically the original system. So what I mean by that is you can kind of change the structure, but the only thing that is important to note here is that your controller will include this whole structure here, and only this is the plan. Only this part is the plant. So the model itself, the part without the delay, and the controller itself will construct the controller structure. So you will connect this as a controller. So it's a high order approach because that's another similarity with the model matching controller. Because you have the model itself, and that's not even enough. You have the non-delay part, the part without delay in the controller, embedded, and then your controller. And you can use any controller, any classical controller. So you might have a PI controller here, which even increases, even more increases the degree of the controller. So this is a high order method, basically, compared to the Pade approximation method. You might say the Pade approximation uses more and more poles and zeros, but I will argue with that because that's only for the synthesis or analysis part. And once you're done with that, you have a controller that is just P or PI or PID. So those high order approximations are used as a plant, not as a controller. But in this case, we are using it in the controller. So there's a big difference between those methods, between the Pade approximation and then designing a controller to that approximation and plugging it in to the original system is much different than this method because this method includes those approximations in the controller. So that's very important here. And if this approximation is not good enough, then your controller will mess up. But if you're using the Pade approximation, you already validate your design. So if the design is not good, the only responsible person is you as the designer, because the control structure doesn't include the model of the system, and you should check your closed loop design, and if it's not fit, you should repeat the control method. But in this case, you might go ahead and repeat your model identification step, because this has nothing to do with the controller itself. This is only the structure of the system and then your controller. But if you're not able to design a good controller, then you're not able to handle a delayed system, because without the delay, just a basic system should be controllable by the designer so that the closed loop behavior and specifications are met. So basically, if this response messes up, the controller can be responsible, but that's not most probably the case, because you should try your best for the design. So this means that probably your model is not the best model or has some restrictions in it, and you should try to repeat your model identification step, whether it is a mathematical modeling or identification. It doesn't matter. So if you construct a structure, if you use this plant, if you have here a plant, and if you use a mathematical representation that includes the delay, and you're basically subtracting it from the actual response, and then you're adding the non-delay part to it and feeding it back to the controller so that the controller is using the non-delay part for feedback. So what this structure does is basically you will get rid of the delay part. So if you have a system like we have here, like this one here, you're just not paying attention to this e to the power of minus 2s. you're designing a controller just for the non-delay part, or for the part where we don't include the delay. And once you're finished with your design, you go ahead and look to the structure and construct the same structure, and hope that it will work. That's it. Because this method doesn't include a design for the delay, because the structure itself handles the delay part. You will only design your controller for this part. So this is the reason why I'm going to skip D, because you should be able to design a PI controller just for 12 divided by s plus 4 times s plus 6. And constructing this structure might be possible by using Simulink, because you can go ahead and use Simulink and place the system, copy the system and place the same, and then place a transfer function that is only 12 divided by s plus 4 times s plus 6 for this system, and make the connections, which are very simple, and then connect your controller and feedback structure, and that's it. You can just observe the output if it's working or not. Now let's go over my solution manual that I've prepared for this, and you can see now that it's a more formal prepared solution manual. You can see what the poles and zeros or the polynomials corresponding to the poles and zeros coming from this approximation look like. And then you have the mathematical code. We've generated this plot. We've also generated this plot, kind of, but I have plotted them here separately to emphasize that we are adding poles and zeros on the real axis or complex conjugates. It depends on the approximation that you use, and then we've code for that, and then we use the root locus plot here. This root locus plot gives us some intervals, but these intervals are not applicable using in the first order, but it is sufficient to use the second order, and then you will get the response here. Now here I have also included the designs that I have told you about. Remember that we were asked to design a 10% overshooting PI controller. If you use the PI controller, you can just use this plot here by adding the S to the system, and then just plot the root locus and try to place 0, etc. I guess I have placed it so that I was cancelling out -1, which comes from the approximation. So there are many tools. You can also just use the usual PI control methods, PI controller design methods, basically. But I have just used one, and these responses include the first order Pade approximation, second order, and the original system. And what I was trying to tell you here was that this blue plot should always exist. Maybe these red and this green or orangish, yellowish, not green, sorry, yellowish, orangish plot and this red plot are not that necessary. But this blue plot, which is basically the controller and the delayed system, so 12 divided by s plus 4, s plus 6 times e to the power of -2s, and the controller in the closed loop should be plotted for validation. You should check out if your design works or not. This is called validation, and you should validate your controller on the system itself, not the Pade approximations. Okay, it is really important, and the original system should be plotted. So maybe it is a good idea to note that never ever plot the Pade approximations, because if you're using Pade, you are assuming that you are good at it. So it's not really that important to plot the step responses, because if you're using Pade, you're approximating the part of the system, and then you're trying to use dominant pole placement or model matching, whatever you use, in order to get a certain controller. And then this controller should be connected to the original system, and you should look for that closed loop response. So these red and yellow step responses doesn't mean anything for me, because those are not those are nothing else than mathematical representations. They don't exist. So what exists is that blue line. So this blue line, this blue plot, which is not that visible here, is the real system. So you should go ahead and look for the real system response. By the way, it might be the case, and it should most probably be the case if you're designing a controller, that your Pade approximation gives a similar response. That should be the case, but checking out the approximation might confuse you. Just get rid of these and just look for the original system if you're looking for the feedback. Now, I've shown you this structure, but it is also possible to work out the closed loop transfer function, and I will show you this here. So what I mean by GMS is basically this is the motor or the model that has delay in it, that is nonlinear, that exists in the real world as a physical process or system. Now, the part where I use G0 times e to the power of minus tau s is a mathematical approximation of that system. I'm sorry. And in the ideal case, these should be equal to each other if you have a nice model. So this comes from the identification method. This is the original system, and this is the identification used model. Okay, so I have an inner loop with the controller and GM, and then this is with a other loop where G0 is there. So basically, you can look for the structure and this transfer function and try to understand what's happening, or you might look at the structure, use pen and paper, just sketch that connection and try to work out the closed loop transfer function. And this should be the transfer function expression that you come up with. Once you do the necessary steps in order to get the actual transfer function, you get this expression here. Now, if you look at this expression, we have fs g0 e to the power of minus ts, which comes from the fact that in the feed-forward path, you have the plant, GM, and the controller, or the model or process that exists, and your controller is in the feed-forward path. Since in the ideal case, and I have this here, in the ideal case, this should be equal to GM. We have here this value here, G0 e to the power of minus tau s. And then we have a denominator that looks like the following. We have 1 plus f times G0, which is basically telling me that I am trying to design a controller for G0 divided by 1 plus f G0. And then I have here the physically existing system and the mathematical model as a difference multiplied with fs. So this means and tells me the following. If Gm is equal to G0 times e to the power of minus tau s, then this whole term will vanish. And if this vanishes, you will see that in the denominator there will be no e to the power of minus tau s term, which means that this is no more a quasi-polynomial, but in fact it is a polynomial. And it's usable for the design methods that we've learned up to this point. So, and if you look close for the closed loop transfer function, you can see that the denominator fg0 divided by the numerator fg0 divided by the denominator 1 plus f times g0 is basically the usual closed loop that I'm designing without delays. So this part is basically the same part where we have a control design for a system that doesn't have any delay. So in the previous lectures, we always came up with fg0 divided by 1 plus fg0, since g0 doesn't include any delay terms. But then we added a e to the power of minus tau s. So if you remember, I did did look for the response, and I had G0, and then I added GS0, and then I added the delay part, and GS was the result of that. Now, this seems like that I have a closed loop, TS, and I have multiplied TS with e to the power of minus TS, minus tau S. So what I mean by this is it is an input-output delay at this point. So you design a controller, and then you are adding the delay part to the closed loop directly. So this structure helps you so that this is possible. Normally that's not the case because you don't have the G0 part here, you don't have this part here. Most of the time you will have this divided by this term here, which includes e to the power of minus tau S. So with the Smith predictor, the nice thing about this is if you know the structure and if you get the idea behind this structure, then the only thing that's left to you is to design a controller for the non-delay part and just plug it into this structure, and your result will be 2 seconds for our controller or tau seconds for any system. It will be shifted with the amount of delay in the closed loop. So that's really important. And you can see now, if the ideal case appears, then you will have this closed loop and you will have this delay part that's sitting there separately. So it is very nice, and you will go ahead and come up with a design. And this is the closed loop step response using the Smith predictor. So basically you have a delay in the closed loop, but everything else is as usual. So you're just shifting it by a delay. Now, what happens if you have some imperfections? And let's say you don't know the exact amount of delay. Well, your structure doesn't work very well because after some time, the effect of the delay error or the difference in the delay in the model and in the plant will give you a adverse effect that looks like this. So the Smith predictor has a drawback, as you can see here. If you don't know the delay exactly as a value, maybe Smith predictor is not good for you. You should go ahead and try to use some Pade approximations and some validation steps in order to get a feasible solution here. So it is very simple to design a controller and using the Smith predictor because those are separate steps. You are designing a controller for the non-delay part, and then you're going to construct a structure that includes that delay part, the plant, the mathematical models, everything, and you will end up with a design that is suitable for delay systems. So this is kind of the model matching version that is used for the delayed transfer functions. But the Pade approximation has some advantages, such as using the root locus. It is possible to use the root locus. Its design is not that sophisticated. It's not that complex. You can just go ahead and get the idea because you know what the transfer function looks like that you're trying to use for your design. The drawback of the Pade approximation is that you will need higher order approximations, but most of the controllers that we've seen up to this point doesn't have that much degree of freedom. So the higher the Pade approximation degree, the more difficult is the design process. Since, as you might remember, if you plug in 10 or 20, you will have 10 or 20 poles and zeros in the complex domain, and then also they will tend to each other, and we've seen that in the root locus that was the case. So basically, if you have a very good idea about the system model, and if you did your model identification step very well, then you might go ahead and give the Smith predictor a chance. The prediction part, by the way, comes from the fact that it uses the delay and subtract them, and then it uses the non-delay part and adds that, and then gets the feedback result. So basically, the delay part is eliminated, and you're kind of predicting the output, since you are getting rid of the delay part. It kind of is a prediction of the output that would have been the case without delay. So basically, that's that. And for both of them, for both the Pade approximation and the Smith predictor, you should always check your controller performances on the original system, not the Pade approximations or not on some approximated transfer function. Always use the original planned, the more mathematical model for validation steps of your controllers. So basically, what we've learned today is that we have learned that there is a Pade approximation that helps us out to maybe use the root locus for delayed systems, maybe to calculate an interval and a stability interval for delayed systems. Since we are not able to plot the root locus of a delayed system directly, it is handy sometimes to use some Pade approximations. A system with delay in the closed loop has infinite amount of zeros and most probably also infinite amount of poles, and most probably also infinite amount of zeros. So this is, as I've told you before, is an issue. But if you use approximation, you're just taking a certain amount of elements out of those possibilities and design it. So basically, there are two methods that we've seen for now. In the next lesson, we will be talking about the frequency domain approaches. So basically, this will conclude our time domain lessons. We will switch to the frequency domain, and then we will look for most of our controllers. We will look at the design of those controllers in the frequency domain. And after the frequency domain, we will get to the state space methods, and then this basically lecture will be concluded for our semester. So hope that everything was clear enough, and we did get a nice bit of information. Hope you healthy and enjoyable days, and see you in the next lecture.